Hi everyone. In this video, I am going to explain about the realization of CMOS NAND gate. In the previous video, I told you how to design this CMOS inverter. So basically, CMOS consisting of a PMOS transistor circuit and NMOS transistor circuit. So CMOS consisting of PMOS and as well as NMOS. Okay, don't call CMOS transistor. CMOS is a device consisting of two transistors, PMOS and NMOS. It is not a transistor. Okay, so PMOS should be connected in pull up and NMOS devices should be connected in pull down, as I said earlier. Okay, now here our gate is NAND gate. Let us consider the realization of two input NAND gate. Two input NAND gate. So two input NAND gate means it is nothing but AND gate followed by NOT gate. AND gate followed by NOT gate. So this is A, B and gives output Y is equal to AB bar. In normal realization, we are first taking the AND gate followed by NOT gate. You can also draw the same circuit much more elaborately as AND followed by NOT operation. Okay, AB, and this is AB up to here. After this, it is equal to AB bar. But in our CMOS realization, as it is a complementary metal oxide semiconductor, the output is a complemented form for the input realization whatever you are doing. Okay, suppose if you are doing two input NAND gate, so you are taking two PMOS transistors, two NMOS transistors, and you are realizing the circuit. Thereby, the output is NAND directly it is coming out. Okay, we are not intentionally doing complement action, but automatically the complement action is coming from the basic circuit itself. Okay, that means in the complementary metal oxide semiconductor logic families, the outputs are always complemented forms. If you want to go for the true form, then you have to use an inverter at the output. Okay, opposite action for the general realization. In the general realization, first you are getting the true form. After that, you are taking an inverter to get the complemented form. But in the CMOS logic families, first you are getting the complemented form. Later, you are getting the true form by adding an inverter at the output. Hope it is clear. Okay. Now, for our two input NAND gate, how many inputs are there? Two inputs are there. So, two inputs means two inputs means two PMOS transistors we have to use and two NMOS transistors we need to use. How to connect the PMOS transistors? It is a product term. It is a product A into B. This product gives PMOS transistors must be connected in parallel for product realization. Okay, so PMOS transistors must be connected in parallel for product realization. NMOS is always opposite is the case. For the same, NMOS should be connected in series. Remember, the realization of the PMOS logic is opposite with the NMOS logic. And similarly, NMOS logic realization is opposite with the PMOS logic. Remember only one thing that is sufficient so that opposite is the action with the other logic. Okay, suppose if you are remembering in a product configuration for PMOS transistors, you have to connect them in a parallel realization. Okay, then when PMOS transistors connected in parallel, automatically NMOS should be in series. No need to remember the second one. Only one is sufficient. Suppose if you are remembering that the NMOS transistor should be connected in series for product, then the PMOS transistors must be connected in parallel. Opposite is the case. Remember only one thing. Both if you remember, definitely you will get a confusion. Okay. And suppose if it is a plus realization, in the plus realization, PMOS transistors should be connected means two transistors are there, so two transistors must be connected in should be connected in series, because PMOS transistors are connected in parallel for product. Here they must be connected in series for plus. Okay, and for the same, NMOS transistor should be connected in parallel. Okay, if you reverse, then the operations are different. Okay, suppose in you are intending to draw NAND gate, but you have connected PMOS transistors in series, then it will give NOR operation instead of NAND operation. Okay, that you have to take care of. Now let us draw, with this knowledge, let us draw the CMOS 2 input NOR gate. So CMOS 2 input NOR gate, PMOS transistors must be connected in parallel. PMOS, this is going inside, this is coming outside, and here it is the input. And take another transistor which is in parallel with the first transistor. This is outside, this is inside, this is another transistor. Name this as A and name this as B. Parallel means both the ends, source and drain, must be connected together. This is VDD. Okay, already we know PMOS transistors or pull-up transistors must be connected between VDD and output. This is output. Now, between output and ground, you have one more realization, that is made up of NMOS transistors. So that those NMOS transistors must be connected in series. Here it is going inside. This is A, this is B. Okay, this is called CMOS NAND realization, 2 input NAND realization. Here output is equal to A into B whole bar. Directly the complemented form is coming out. Okay, if you have any doubt, you can check the operation. Let us consider what happens when input is equal to A is equal to 0, B is equal to 0. Okay, there are 4 different cases. Let us take the first case. A is equal to 0, B is equal to 0. A equal to 0, B equal to 0, what happens? That makes the PMOS transistors take Q1, Q2, Q3, Q4. As there are 4 transistors, 2 PMOS and 2 NMOS, let us name with Q1 and Q2, Q3 and Q4. So when A equal to 0, B equal to 0, Q1 on, Q2 on. What about Q3 and Q4? Off. So as Q1 and Q2 are on, it is having a short circuit path here between output and VDD, and it is completely open circuit on the other hand. On the other side, it is open circuited. So there is a connection between output and VDD. So Y is equal to logic 1. Y is equal to logic 1. If any one of the PMOS transistors is in on state, listen clearly. If any one of the PMOS transistors is in on state, then there is a connection between VDD and output. Then definitely output becomes 1. This happens if either of the transistors is in on state. That means if A is equal to 0 or B is equal to 0 or both A and B are zeros. Hope you understand. Okay. So second and third cases I am taking at the same time. A is equal to 0, B is equal to 1, and A is equal to 1, B is equal to 0. Both gives the same result. Both gives the same result because that makes either Q1 or Q2 on. See, A is equal to 0, B is equal to 1 makes Q1 on, Q2 off. A is equal to 1, B is equal to 0 makes Q1 off, Q2 on. Whatever it is, there is a connection either through A transistor or there is a connection either through B transistor to the output. In that case, definitely it is 1. And in the bottom part, if you see A is equal to 0 and B equal to 1, even Q4 is in on, Q3 is in off. And A is equal to 1, B is equal to 0, Q3 is in on, but Q4 is in off. So as one of the transistors is in off state, always there is no connection between output and ground. So definitely we can eliminate the bottom part. Only we will be having a VDD and output link. Then we will be having output is equal to logic 1. Hope you understand. In this case, Q1 on, Q2 off. What about Q3? Q3 equal to 0 means off, Q4 on. And here also Q1 off, Q2 on, Q3 on, Q4 off. So simply what happens? In this case also there is a connection between output and VDD, and there is no connection between output and ground. So I is equal to 1. If you go to the last stage, A is equal to 1, B is equal to 1, then what happens? Q1, Q2 off, but Q3, Q4 on. So that's why VDD has no connection now. It is simply open circuited. But whereas in the bottom case, both the transistors are in on state. So Y is equal to 0. Okay, if you take truth table for all these, it gives NAND operation 0 0 0 1 1 0 1 1. For first three cases we have got 1, and the last case it is 0. Okay, this is nothing but NAND realization. For AND operation, when all the inputs are 1, output is logic 1, but here when all the inputs are 1, output is equal to logic 0. Okay, in the next video I will explain about CMOS NOR realization. Thank you.